think. Okay, all right, yeah. So welcome everyone to the third installment of the Capsule Talks this semester. So today we have two talks. The first speaker is Christina Karafyllia. So she's a Milner lecturer in the department, a new one, and she just comes off her PhD in Greece, in Thessaloniki. And well, her title is Conformal Invariants in Spaces of Holomorphic Functions.
Hello, everyone. Thank you for giving me the chance to talk about my research in the department. Today, we're going to talk about conformal invariants in spaces of holomorphic functions. Conformal invariants are quantities that remain invariant under conformal mappings. And when I say conformal, I mean a one-to-one and holomorphic function in the complex plane. Some of the most well-known conformal invariants are harmonic measure and hyperbolic metric. And today we are going to see how we can use them in order to give geometric conditions for a conformal mapping to belong in some spaces of holomorphic functions, such as Hardy spaces. So let's start with some definitions. Okay, first is the definition of harmonic measure. I don't know how can I hide this. Okay, first we'll define it in the unit disk. So we consider the unit disk and the Borel subset of the unit circle. Let's call it E. Then the harmonic measure of the set E at the point 0 in the unit disk is actually the normalized Lebesgue measure of E. We can extend the definition of harmonic measure in every simply connected domain by using the Riemann mapping theorem. So in general, we have a simply connected domain D. In this talk, we are going to talk only for simply connected domains, and the Borel subset of the boundary of D, and the point Z in the domain. So the harmonic measure actually depends on two variables. The first is a point, and the second is a set. And it is conformally invariant, and it gives us the probability of a Brownian motion starting from Z to exit from the domain D, passing through the set E. Okay, so just keep in mind that it's conformally invariant, and it gives us the probability of a Brownian motion starting from Z to exit from the domain through E. This means that when Z, the point Z, is close to the set E, then the probability is very high, so harmonic measure tends to 1. And when Z is far from E, then the probability is very low, so the harmonic measure tends to 0. That is the probabilistic interpretation of harmonic measure, and I think it's the simplest way to describe this. Now, the other conformal invariant quantity is a hyperbolic distance that comes from hyperbolic metric. So again, we'll define it in the unit disk. We consider 2 points in the unit disk, Z and W. Then the hyperbolic distance between these 2 points is given by this logarithm, and we can extend again the definition in every simply connected domain by using the Riemann mapping theorem. And the last definition we need for today is the definition of Hardy spaces and the Hardy number. Hardy spaces are spaces of holomorphic functions and are the most known from these spaces. For a positive number P, the Hardy space with exponent P is denoted by HP and is the set of all holomorphic functions F on the unit disk that satisfy this property. So we actually consider the value, we take the values of the function F on every point of the circle with center at 0 and radius equal to R. Then we integrate and we take the supremum over R. And we actually interested in what happens when R tends to 1. So intuitively, the fact that a function f belongs to some hard spaces imposes a restriction in its growth. And this restriction becomes stronger and stronger when the exponent p increases. This means that if p is greater than q, then hp is contained in the space HQ. We'll see some examples in the next slide. For a conformal mapping F of the unit disk, we can also define the hard number of F, which was first introduced by Hansen in 1970. The Hardy number is the supremum of all exponents p for which the function f belongs in HP. And in case of conformal mappings, it's a real number over than or equal to 1/2 or infinity. So the definition means that for every p less than the Hardy number, f belongs in HP, but for every p greater than the Hardy number, f doesn't belong in HP. But what happens when p is equal to the Hardy number? In this case, there's not a general rule, but it depends on the function f we have to study, and we'll see some examples in the next slide. So let's see examples. We consider simply connected domain D and the Riemann mapping F from the unit disk onto the domain D. So if D is bounded, then the Hardy number is always infinity, which means that F belongs to every Hardy space HP. So bounded functions belong to every HP space. When D is a sector, for example, with angle equal to alpha, then the Hardy number is equal to pi over alpha. And this means that when alpha decreases, the Hardy number increases. So F belongs in more Hardy spaces. When alpha is equal to pi, we have the right half plane. And this is an example where F, it's the Riemann mapping, F doesn't belong in HP, where P is the Hardy number. And this is another example where F belongs in HP when P is equal to the Hardy number. And these two examples answer to the question I posed previously. Answer to this question. So it depends on the case. There's not a general rule for this. This is some examples of functions and how they behave according to Hardy spaces. Now, in general, there is not a formula to find the exact value of the Hardy number. It's very difficult to find this number. There are only some lower and upper estimates, mainly proved by Hansen, but not general formula. There are also some formulas, but only for specific domains, like star-like domains and spiral-like, but not a general rule. So it's difficult to find this number. Also, as you can see, it's difficult to use the condition of the definition to check if a conformal mapping belongs in HP. To estimate this integral, the supremum of this integral, we need to know F, and this is very rare. In most cases, we don't know F, but we know its existence. So today, our goal is to replace this condition with a more geometric condition that involves harmonic measure and hyperbolic distance, which are directly related to the geometry of the domain of the image region of the function f. And also, we are going to find some formula for the Hardy number for the case of conformal mappings by using the same quantities. So, the motivation to study such kind of problems was two questions of Pozzi Corradini in his PhD thesis in 1996. He was a student of Donald Marshall. So let's see the background of these questions. First, we consider a conformal mapping psi of the unit disk onto an unbounded simply connecting domain D. And for a positive real number alpha, we define two sets, F alpha and D alpha. I will describe these sets through this image. Here is the unit disk, and here is the domain D. So we take the circle with center at 0 and radius equal to alpha, and then we consider the intersection of this circle with the domain D. In this case, the intersection consists of 4 components of these 4 red arcs. The pre-image of these arcs is the set F alpha. Also, we consider the part of the boundary of D, which lies outside the disk with center at 0 and radius equal to alpha, which I noted by blue color here. And we take the pre-image of this set. The pre-image is the set E alpha. So, as you can see, despite the fact that we define these sets in the unit disk, they are studied more easily in the image region D. That's why we need to use conformally invariant quantities. We want to be able to transfer from the unit disk to the domain D and conversely. So keep in mind the set F alpha and D alpha, or better psi F alpha and psi E alpha. Pozzi-Corradini made 2 observations. The first is that by a very well-known theorem of Berling and Ivan Lina, the projection theorem, it follows easily that the harmonic measure of the set F alpha is greater or equal to this quantity that contains the hyperbolic distance between 0 and F alpha. So there is a relation and an inequality between harmonic measure and e to the minus d, where d is the hyperbolic distance. That's the first observation. And he also proved that conformal mapping psi belongs to some space HP, even only if this integral is finite. And this integral contains the harmonic measure of V alpha, of the center that we defined previously. Or we can check this integral, where this time we have to estimate the harmonic measure of F alpha. So he gave a more geometric condition to check if a conformal mapping psi belongs to HP. It's much easier to use this condition because now we only need to estimate the harmonic measure, and there are various ways to do this. And I also want to mention that this equivalence is not so obvious because these 2 harmonic measures are not comparable in general. So, based on these 2 observations, he made the following questions. The first question is whether there is a positive constant such that the opposite inequality holds. That would mean that the harmonic measure and e to the minus d would be comparable. And the second question is whether we can replace in this condition the harmonic measure by e to the minus d. So these are the questions. This is the first one, and this is the second one. Of course, if the answer to the first one is positive, then the other is proved very easily. But if it's negative, we can't understand what happens here, if this is true or not. So let's start to see the answers. The answer to the first question, is negative, because, and this is because of 2 phenomena that we're going to see very briefly. This is 2 counterexams that show us the reasons for which the answer is negative. This is a star-like domain, and we take the set CF alpha. In this example, the number of components of psi f alpha tends to infinity as alpha tends to infinity, because the domain has more slits as alpha tends to infinity. So the number of these components, when we consider this circle, increases. That's the reason for which the answer is negative. Now, the other counterexample is this. In this example, despite the fact that the number of components of psi f alpha is finite because there is only one component here, the answer is still negative because here there is a sequence of alpha n such that the hyperbolic distance between the arc psi f alpha, which is denoted by red color, and the hyperbolic geodesic joining these endpoints, the hyperbolic distance between these two curves tends to infinity as alpha tends to infinity. And that's the reason for which the answer is negative. So if these two phenomena do not occur, only then we can compare these quantities. Only then they are comparable, but not in general. So the answer to the first question is negative. These quantities are not comparable. So one would expect that the answer to the second question would be also negative. But the truth is that the answer is positive. So we can obtain another geometric condition for a conformal mapping psi to belong in some space HP. But this time, we don't need to estimate the harmonic measure, but the hyperbolic distance. And that's useful and very helpful because the hyperbolic distance is directly related to the quasi-hyperbolic distance, which contains only Euclidean distances in its formula. So if we want to check if psi belongs in HP, we don't need to know anything about psi, just to study the geometry, the Euclidean geometry of the image region D, of the simply connected domain D. Because D is conformally invariant, so we can go from the unit disk to the simply connected domain D. And I just want to mention that this equivalence, this condition is generalized to Bergman spaces, which is a larger class of spaces of holomorphic functions, and Bergman spaces contain Hardy spaces. But I don't want to say more about this. So we saw that these quantities are not comparable in general, but when we integrate them, then the integrals are finite or infinite at the same time. The only thing that remains to study is what happens with the limits of these quantities. Do the limits give us something interesting or not? When in the start of the talk, I told you that it's difficult to compute the Hardy number in general, but in case of conformal mappings, Kim and Sugawa proved that the Hardy number is given by this lim-inf. Again, in this lim-inf is involved the harmonic measure we studied previously. And it is also proved that the Hardy number can be given by this lim-inf, where this time, instead of harmonic measure, we have to estimate to find the hyperbolic distance. So, in conclusion, what we did today is to find ways, geometric ways to check if a conformal mapping belongs to the Hardy space HP or not. The first way is to check if this integral or this integral with harmonic measure is finite. And the second way is to compute this lim-inf and find the Hardy number. In both cases, we only need to study the geometry of the simply connected domain D and estimate the harmonic measure on hyperbolic or the hyperbolic distance. And then, as I told you before, there are several ways to do this. That's all I want to say for today. Thank you for your attention.
Okay.